6 next week on Tuesday, Wednesday, Thursday, and Friday. And there are several presenters in the audience I can see already. We got Bennett here, and we got Mike, and there are a few. Oh, they're Matt. No, presenters everywhere. Oh, Matt just finished presenting. Excuse me. He was this Tuesday. Anyhow, want to invite you to that. Number one. Number two, it is live streamed so that that if you've got a friend, you can text them, and they can't make it, they can at least watch it in their room. And if they missed that, it's also on YouTube. So you can search Laureate's Chemistry Senior and it will come up. It may take a couple hours before it actually gets up because I have to upload it. But anyhow, I wanted to let you guys know about that and come next week. Okay? Anyhow, it's my great pleasure to introduce Rachel. So Rachel is another one of my advisees. I'm losing so many advisees this year. But that just means it'll be a lot easier next year. No. Oh, no. I'm on sabbatical in the fall, so I don't get any freshmen. That's what I mean. Anyhow, it's been a pleasure having Rachel as an advisee. I was a little surprised to discover her dad is a chemistry professor down at Knox. And so I was like, wow, chemistry professor trusts us to teach his child. This is cool. And it's been really nice having Rachel around. As Chelsea had served as Olivia's mentor, and Olivia's my daughter, mentor for swimming, Rachel serves as math tutor mentor. And yes, this Wednesday we will be around. Long story. But anyhow, it's been a pleasure having her as an advisee. She's going to be headed off to graduate school at UC Davis doing very similar things to what she's going to talk to you about today. She has fallen in love with solar cells, and I suppose it's a bright future for her. Very good. Rachel.
Hi, I'm Rachel, and I'm going to tell you all about the research that I did this past summer at the National Renewable Energy Lab about solar cells. So this is called Seeking Maximal Efficiency of Thin Film Photovoltaics through Deposition Method. So the photovoltaic cells are solar cells, so I made solar cells. I'm trying to maximize how well they work by depositing my materials in different ways. So first we'll start really broad and we'll talk about energy. So there's two different types of energy sources. There's renewable energy on the left and non-renewable energy on the right. And so non-renewable energy sources means that the rate at which we use it is faster than the rate at which it's naturally replenished. So like coal or natural gas, for example, took about 300 million years to form from dinosaur and plant bodies. And so the rate at which we're using it at tons and tons per day is way faster than the very slow rate at which it's coming back. So it's non-renewable. We also have nuclear energy, where you shoot a neutron at a radioactive element and split it into atoms of a different element. And it releases this huge amount of energy, which is almost impossible to put back together. And so that means that the rate at which it naturally is replenished is 0. So however fast we use it, it's faster than 0, non-renewable. And then we also have renewable energy. So there are 5 major sources of renewable energy. The first one is biomass, which is people waste and animal waste and industrial wood scrapping waste that we convert into biofuel and we combust. So it's a lot like burning fossil fuels, but it comes from a waste source that we're using up. Then we have geothermal energy, which means heat that comes from the earth. And so if you dig about 6 feet down in the ground, the temperature of the earth is very, very consistent. Depending on your latitude, somewhere between 40 and 50 degrees Fahrenheit. And so you can use this very consistent temperature and tap into it to keep your house at a consistent temperature. So you can cool it in the summer and heat it in the winter. We also have water power, where we harness the motion of water using turbines that spin and making energy out of it. So you can use falling water like in a dam, you can use ocean power in the waves that move the turbines up and down, or you can use tide power, where it flows in and it flows out. I don't imagine that gives you very much energy, but someone has invented the technology. Then we have wind energy. I'm sure you've seen the turbines out in the Wisconsin countryside, where the wind turns the blades make kinetic energy, and the kinetic energy is transferred to electrical energy. And then we have solar energy, which is obviously the best type. So solar energy comes from the sun. And the sun radiates a lot of different kinds of energy, photons. And so the bottom axis, the x-axis represents wavelength. And so on the left end, the lower wavelengths represent the highest energy. And so when sun hits the Earth at the top of the atmosphere, the black line stands for that amount of energy. And then the red shaded section, laser pointer, the red shaded section represents the amount of energy that hits the Earth's surface. And so everything that you see in yellow is the difference that the atmosphere absorbs. And so what happened to all that energy? Ozone absorbs a lot of the ultraviolet light, and water vapor and carbon dioxide absorb most of the infrared, which is where the greenhouse warming effect comes from and why our Earth is warm enough to habit people. And so when we design a solar cell, we want to pick photons in the visible range, because visible are very abundant, as you can see from their high score on the spectral irradiance y-axis, and they're also high energy. So we can make an efficient cell, and there's enough photons that we can make it worth our effort. So when a photon from the sun hits a material, it excites an electron from the lower band, called the valence band in blue, to a higher band called the conduction in green. For all you chemists out there, this is like the HOMO-LUMO gap, exciting an electron from the highest occupied molecular orbital to the lowest unoccupied orbital. So, back to physics. So we have an electron, and we want to excite it from a low to a high band. And the difference between the band, the amount of energy that you need, is called a band gap. And so depending on your material, your band gap has a different size band gap. So if I was to use metal, you can see the band gap is almost non-existent because the layers are actually right up against each other. And so any photon walking along can excite a metal, which is why it's so conductive. If I picked an insulator material, then it has a very large band gap. There's a very large space, you need a very high energy photon. So when you pick up your hot coffee off the stove and you use a hot holder, because it takes a very specific photon that you don't encounter very often to get it excited and make it hot. And finally, we have a semiconductor, which is what I choose to make mine, because it's a nice balance between any photon and every photon exciting it, and only one very, very rare photon. It's a very small size band gap, and this happens to be the size of visible light. So there's two different kinds of band gaps, a little bit more physics. So there's a direct band gap and an indirect band gap. So direct band gap materials are the easier ones. You just excite it from the lower level to the higher level by a photon, no problem. Your indirect band gap absorber, before you excite it, your electron has to change momentum to get into that top layer. And so when it changes momentum, this takes time. And because it's moving at a fast speed, this takes space. So when you build your indirect band gap cell, it has to be several inches thick to make sure that the electron gets excited before it leaves the material. And my type of cell is a direct band gap cell, so I can make it very, very thin, a couple nanometers, and not have to worry about it. So a photon excites a material, excites an electron from the middle layer, purple, up into the top layer. So the electron goes into the top layer, which is called N-type for negative, and the electron leaves behind us an open space, which we call a hole. And the hole is positively charged, so this layer is called the P-type layer. So the electrons move in a circle around the cell, and they move through the load, the most important part, which you know as the battery, or the light bulb, or the little fan that spins, the exciting part. And so we have to be very careful designing the lifetime of the electron. The lifetime is how long it takes the electron to relax back down to the lower level. Because if the lifetime is too short, then the electron is going to relax back down before it even gets to the light bulb. And so there was no point in exciting it. And if the lifetime is too long, then it runs all the way around and it's finished, but it's still excited. It's like when you try and do homework with Facebook open. You have a potential to be way more efficient, but you're just holding yourself back by leaving it open right there next to you. So now you know how physics works and how solar cells work a little bit. So this is why you would choose to use solar panels if you're not like super pumped about them like I am. So first of all, the sun. There's a lot of energy coming out of the sun. 3.8 times 10 to the 26 joules hit the Earth's atmosphere every single second. This is the same amount of energy that we've been using ever since we invented electricity back in the 1800s. Every single second. It's a lot of energy. And then the amount that hits the Earth's surface, if we could capture 1 hour of that energy, it could power the whole world for a day. So we don't even have to have 20% efficient or 50% efficient. We just need to have a high enough percentage of coverage on the Earth and a high enough efficiency that we can capture enough of the energy. Solar energy is also renewable, like I said at the beginning. It's low maintenance, unlike water power, because it doesn't have any moving parts, except for little kids who throw baseballs at it. It has no dangers. They're non-polluting, unlike biofuel, which still involves burning things. It doesn't pollute the air, it doesn't pollute the liquid water in the ocean, and it doesn't pollute the soil. And it's also silent, unlike wind turbines, which make really loud whoosh noises and kill birds. So why doesn't everybody have a solar panel on their roof if they're just that awesome? Well, there are several challenges, not problems, they're challenges with making sense. The first challenge is a phenomenon I'm sure you're familiar with. It's called night. This is the time of the day when the sun is not shining, and so we can only harness the solar energy when the sun is hitting the cell. And also, the amount of sunlight per day varies with your season and your location. You may remember the absolutely awful winter we just experienced, where it was very, very cloudy almost every day. So solar panels in Wisconsin face a lot of challenges, not problems. Solar energy is difficult to capture because when you design a cell, you design it to absorb a single wavelength. So I highlighted the visible range in the early slides, which is 400 wavelengths, but we can only design it to absorb one. So one cell can never absorb as much energy as my big fancy numbers at the top of the slide. There's a theoretical limit when people who are really good at math do calculations about the best possible efficiency a solar cell can be. They came up with 34%. So no matter how good your materials are or how carefully you put it together, you can never ever make a solar cell that's better than 34%. They're also expensive because silicon and other materials are expensive to come by, and it's not always sustainable because sometimes we use materials that are rare and might eventually run out. So I can't fix all of these challenges. I can't take away the night. I can't make the winter any warmer. I'm sorry. But the two things that I can fix are how expensive the material is from the amount of labor and the kinds of materials, and I can pick materials that are more sustainable, that won't run out in 30 years. When a chemist wants to build a solar cell, it's a toss-up between good categories and bad categories. Of course, you want to make a really efficient cell, and you want it to fit its application that it was built for, be it solar panels on your roof. They have window pane solar panels, they have solar panels in your car paint. So you have to design it for what you want, but you have to toss up the fact that people out here like you who earn money and want to spend it on solar cells can afford it, and it's not going to like run out in 10 years when you finally have the money, that you've paid off all your student loans, and that it will last long enough, so that if you put it on your roof, you don't have to replace it every 5 years. I mean, what kind of a pain is that? Even your shingles don't have to be replaced that often. So unfortunately, a lot of the really efficient materials are really expensive figures. So there are a lot of different ways that scientists have come up with solving this problem. And so there are a lot of different types of solar cells. So the one you're most familiar with is silicon cells. These are the ones that you see on most of the roofs. There's mono and polycrystalline cells. Monocrystalline are the ones you usually see. They have nice blue boxes that are separated by white diamonds. And then polycrystalline look a little bit sloppier because they have more cells on top of each other, because they're cheaper to make this way, but they're a little bit less efficient. So again, it's a toss-up. We also have dye-sensitized cells, which have an extra organic dye added to them, so you can specify which wavelength you want to absorb with a little bit more accuracy. And we have quantum dot cells, which are really neat because the technology was recently developed where you can print quantum dots with an inkjet printer. So you can get a piece of plastic and print a whole bunch of little mini solar cells onto it. And so you can design these so that every dot in the row is a different type of solar cell. They each have a different wavelength. So the first one might absorb purple, and the next one blue, and the next one green. And so you can pick up a whole lot of wavelengths with your printed cells. And then we have multi-junction cells, which are pretty much the same as quantum dots, except instead of horizontally, you stack it vertically. So you put a whole bunch of different cells on top of each other, and so when the light comes in from the top, the purple is absorbed, and then the blue, and then the green, and then the red. So it's a lot more space effective, but takes a lot more time to make. It's a toss-up. And finally, we have thin film cells, which are the ones that I was making this summer. So this is a rough, boxy-looking model of the thin film solar cell made out of semiconductors that I made. And to help you follow me through my science talk, I'm going to make the analogy that a thin film cell is like a sandwich. So the bottom layer is a piece of glass called the substrate. This is like the table, the thing that you put all your layers on top of to make the yummy sandwich. And you have the metal, laser pointer, the metal, which is molybdenum, and the top two layers, which are a zinc oxide semiconductor, and these are like the bread. They hold the sandwich together, and they serve as the electrode and the counter electrode for the cell. They're also designed really specifically. The top two layers are designed to be transparent, because a photon of energy comes in from the top and needs to pass all the way down to the blue layer, where the photon excites an electron. And the metal is designed to be opaque, so that the photon does not pass into this layer and stops here at the absorber. The absorber is like the meat of the sandwich. It's the most important part, and it's also the thickest layer. It's about 10 times thicker than all the other layers in the cell, like a really good sandwich. This is where the photon excites the electron, where most of the heavy lifting of the cell is done. And on top of it is the buffer layer, which is the layer I worked on. It's very, very thin, and the cell would probably work without it, just like a sandwich would work without mustard, but it gives it that little extra kick. It makes it better than the other sandwiches, and this one makes my cell a couple percent more efficient than the other cells. So, when you want to build a solar cell, specifically the absorber, the meat layer, you want to choose materials in this box, one of these 20 elements, because they've been found to work the best. And so when you're choosing materials to make your absorber out of, you choose 4 materials. And so you pick 1 material from column 1, 1 material from column 6, and 2 materials that add up to 6. So if I wanted to use, I could use 2 elements from column 3, because 3 plus 3 equals 6. Or I could use 1 from column 2 and 1 from column 4, because 2 plus 4 equals 6. So the current most successful model is made out of CIGS and cadmium sulfide, and that's the one that I'm trying to beat with the research I'm doing. So CIGS is my absorber material. This stands for copper, indium, gallium, selenide. And so you see copper is in column 1, selenium is in column 6, and then indium and gallium are both in column 3, and 3 plus 3 equals 6. So this is an acceptable material, and it works very, very well. It makes 20% efficient cells, way better than any of my beginning cells were making. But indium is a kind of expensive material, and it's also being used up because it's put on every one of your plasma screen televisions. And so there's not a lot left for making solar cells. And then our buffer layer is cadmium sulfide. And cadmium works really well with the absorber layer, but cadmium happens to be toxic to people. And so this makes finding people who want to work with this to make cells kind of difficult if there's built-in occupational hazards. So that's our current model. And so the point behind my cell was to try and find a new material, one that worked just as well as the old one, but I'm trying to fix how expensive it is and how sustainable it is. So the materials that I chose were CZTS and zinc oxysulfide. And for the chemists out there who disapprove of the parentheses, don't worry, I did too. It just means that there's a varying ratio of oxygen to sulfur depending on how you put it down. And so they put parentheses instead. So CZTS is my new absorber layer, and it stands for copper, zinc, tin, selenide. And so copper is in column 1, selenium is in column 6, and then zinc is in column 2, and tin is in column 4. And 2 plus 4 equals 6. So this is also an acceptable material. And you'll notice that zinc and tin, the 2 new materials, are much better than the previous model, because tin is in all of your tin cans that you buy at the grocery store for 10 cents, and zinc is in the sunscreen that you put on your face when it hopefully gets warm out again. And then my buffer layer is zinc oxysulfide. And so this is the really important one. So how did I pick this material? I picked it because I wanted it to work well with the absorber. So if you remember my picture of band gaps, I want you to pretend that this one is the absorber and that this one is the buffer layer. So the most important part of picking a buffer layer is getting the bottom of these green bands to line up at the same level. Because when I excite an electron from the blue to the green, I want to fool it and excite it over to the buffer layer instead, to pass the charge in a circuit through the cell. So I want to align the band gap of my new buffer material with the absorber that I picked. I also want to pick one that transmits visible light, because if you remember, the photon has to make it all the way through the top of the sandwich to make it to the meat, the absorber in the middle, where the action happens. And of course, like I said before, I want it to be non-toxic, cheap, and easy to find on the Earth. And so I've picked my absorber and I've picked my buffer, but now I have to build the cell. And it's not as easy as building a sandwich where you just throw all the stuff together and it looks fine, you'll just eat it. It's a lot more touchy. It's a lot more difficult to do. And so we're trying to achieve these 3 characteristics by picking a different deposition method. So the first one is uniformity. When you put down a buffer layer on top of your absorber, you want it to cover all the whole surface area, because any surface area you don't cover is automatically a dead part of the cell. It's automatically 0. So that's a waste of our time. And we want it to be uniform thickness. So we want the distance between the absorber and the semiconductor to be the same all the way across. So when we make a measurement, we know that it accurately represents how well it's working. We also want stoichiometric accuracy, which means that if my zinc oxysulfide is at a 1 to 7 ratio, then I want to know it's 1 to 7 and not, oh, well, it's 1 to 8, today's not a very good day, or oh, it's 1 to 6 because this instrument's really bad. I want to know for sure how thick it is and what the percentages are. And then, of course, I want it to be easy to do. Not just because it's a pain to sit in the lab for 6 hours and make these materials, but that someday when they're mass produced so that all of you can buy one and put it on your roofs, that it's not crazy expensive, because the easier it is to do, the lower the labor costs and the cheaper it will be. So now we get to the fun part. I chose 3 different deposition methods to test out and compare and see how well they worked. So these 3 methods are atomic layer deposition, ALD, chemical bath deposition, CBD, and partial electrolyte deposition. I'm trying to remember these acronyms as we go because I'm going to be using them a lot. So we'll start with the most difficult one, atomic layer deposition. So this one uses a gaseous precursor to put down the zinc oxysulfide, and it puts it down in cycles. And so each cycle is made up of 2 half cycles, one for sulfur and one for oxygen. And oxygen and sulfur are carried in by zinc, in this case a diethyl zinc. So when you want to make a layer, you flow in the diethyl zinc with the sulfur on it, and you put down a layer, then you purge the chamber to get rid of all the excess little gas particles floating around. Then you flow in the diethyl zinc with water on it to put down a layer of oxygen, and you purge, and then you repeat. And so you have very, very good control because diethyl zinc doesn't stick to itself. And because of that, when you put down a monolayer, you're not going to accidentally get 3 layers because it won't stick. And so you have very, very good score for stoichiometric accuracy and a very good score for thickness and uniformity because it doesn't stick to itself. The only problem is it gets a 0 for easiness because diethyl zinc, if you don't recognize it, is something called a pyrophoric, which means it catches fire when it's exposed to air. So this makes it really expensive to put into a bottle, really expensive to get out of the bottle, and really expensive to train people like me to use it. I never actually got to use this instrument because it takes 6 months to train you and I was only there for 2.5. So it definitely has some occupational hazards associated with it. So the next one is chemical bath deposition, CBD, and this is just what it sounds like. It's like a little bathtub for your cell. You get a really big beaker, you pour in your 3 liquids, you put your cell in for 20 minutes, and when you take it out, your buffer's deposited. And so it gets a really good score for easiness, because I love this one, but it doesn't get as good of a score for accuracy because it does have monolayers that increase to 3 layers at a time. And when you mix the materials in your big bathtub, you don't know if it's uniformly mixed, and you don't know if all of the precursor you put in is going to stick. So it's much easier to do, but it's a little bit more difficult to rely on. And it uses deionized water as the solvent, cadmium sulfate as the precursor, and ammonium hydroxide as the activator that starts the reaction. And the final method is partial electrolyte deposition. And I should be honest with you, this is not actually a deposition method. What this is kind of a wipe. So when you put your buffer on top of the absorber inherently has little hydroxyl groups sticking out from the top that make it really difficult to attach something with a good connection. And so the partial electrolyte is like when you wipe the table with a washcloth before you make the sandwich so that the yuck from the one before doesn't get on the bottom. So we can wipe off the hydroxyl groups in order to make a better connection. So we use this, which is very similar to chemical bath. It has the water, the precursor, and the ammonium hydroxide. And then we use thiourea and DMSO because they're really big, bulky groups that stick out and don't let anything attach to the surface. So we wipe the surface with PE, and then we use the atomic layer deposition from before to actually put down the zinc oxysulfide. It's like a team effort. So once we finish and I've put down my buffer layer, I go into the lab and I put on into the clean room and I put on my white suit with the booties and the hat and the gloves, and I put on these little contacts on the top of the cell. This is what I use to measure it once it's finished. And then I pass it on to my friends Clay and Marty, and they put on the top red layer, the semiconductor, and an anti-reflective coating so that the cell doesn't accidentally reflect all the sunlight and not make it into powder. And so after I've finished taking photos of myself with the cells, then I go and I measure how well they work. So this is called a JV curve, and it comes from an instrument that's called a solar simulator, which is basically a sun in a box, except that because it's not a real sun, it's much more consistent. It has the same wavelength every day, it has the same intensity every day. It's easier than putting it outside on your roof. And so when you measure your cell with the solar simulator, you measure twice for each one. Once in the dark with the light blocked, and once in the light, called illuminated. And you measure 4 different parameters, which I've got up here in this box. The first one is the VOC, the open circuit voltage. This is the x-intercept of your graph. So you've got voltage on the x-axis and current density on the y-axis. So your open circuit voltage is your x-intercept. It's the highest possible voltage your cell can generate. You've also got the JSC, which is short circuit current density. This is the y-intercept, and this happens, we measure this when we set the voltage all the way to 0 and see how much current is still moving in the cell, like when there's no sun shining on it. We have the fill factor, which is the boxiness measure of your curve. You draw the biggest box you can between the x-axis and your illuminated curve, and the percentage of the area under the curve, the percentage of the integral that you cover with your box becomes your percentage. So this one had a 57% fill factor, and this tells you that it's going to be sort of a moderate power level when you finish it. And then the final piece is the efficiency. You take all the factors I just talked about and you multiply them across the top, the voltage, the current, and the fill factor, and this is the power that the cell produces. And then on the bottom, you have the power coming in. And so your efficiency is a measure of, it's a ratio of the power that your cell produced over the total power that it started with. And this tells you how well the cell works. So this one is 9%, which is a little bit better than I've ever actually made. This came off the internet. So I'm about to show you some data. So to help you through, these are the 6 different conditions for the types of cells that I made. So we have white is our control. That's the previous really successful model, the CIGS and the cadmium sulfate. And we have the atomic layer deposition in blue, chemical bath deposition in black, and then the yellow, green, and red across the bottom are all the atomic layer deposition with that extra partial electrolyte wipe to make sure that the connection is better. So this is the data that I measured. We have our 6 conditions here along the side and our 4 parameters here for your viewing convenience. Open circuit voltage, short circuit current, the fill factor, and the efficiency. So right off the bat, if you look at this and try and make a conclusion off of this data as I did, the first thing you notice is that the white dot is winning at all 4 pictures. So this is the control. And so if you figured it out before I mentioned it, this means that my cells are not as good as the one that I was trying to beat. But that's okay. That means that I will still be employed next time. So if you ignore the control and you look at which one of my cells is the best, except for this one, the rest of them, the black one, the chemical bath deposition was the best. And so this tells me that if I were to get some more money to do this again, this is the material that I'd want to continue with because it worked the best, which is surprising since we didn't think that it was going to be the best, it was going to have the lowest accuracy. So if you ignore that one, we can look at the atomic layer deposition. The blue one seemed to be my worst. So it looks like without that wipe, it just didn't do very well. The connection wasn't very solid, the current didn't move very fast. And then if you look at my 3 ratios, the green, the red, and the blue, there seems to be a relationship. It's pretty consistent between the 4 factors. The yellow one is always the best, and then the green one, and then the red one for all 3 conditions. So the yellow one was the lowest percentage. So the one with the lowest percentage, which is the amount, the lowest percentage is the one that scored the best. So in conclusion, the cadmium sulfide, the previous successful model, is still the most successful model. They picked it for a reason. So I'm not done yet, and solar cells are still not defeated. We will continue to fight. And then next, chemical bath deposition was the best out of all the methods that I used. And so this is the one that I choose to continue with because its fill factor and its efficiency looked the best. And finally, out of the 3 different percentages I did, with the PE wipe on the ALD, the one with the least oxygen, with the lowest percentage, was the one that worked the best. So if I were to get more money to work on this again next summer, I'd really love to do more replications. You saw all the dots on the plots. Each of those represented several cells, but when I say several, I mean 2. I only had 2 for each of those 6 conditions because those materials are really expensive to make. And so I'd really love to have 6 or 7 cells in each condition so I could have triplicate to make Deanna happy and to have reproducibility for my data. I'd also love to test out more ratios because I only picked 3 and there's a pretty wide range and you can see that each of those cells perform very differently. And so I'd love to see if that has a real definite connection. And then also, there are other deposition methods out there besides the 3 that I tested. There's something called epitaxial deposition, which is really cool, but is really, really expensive to do. And so undergrads don't get to play with it. And so maybe when I'm in grad school, they'll let me play with other toys and I can continue this study. So I'd like to acknowledge all the people that went into my summer research and went into this, starting with Steve Christensen, who was my mentor, who helped me design the project and taught me all about these materials and why they were good and why they were difficult. And then Conan and Ingrid, who were my 2 PIs of the group leaders, who took me under their wing and fostered a love for solar energy. And so when I came back this year, you all thought that I totally changed. Dave Hall, who listened to me give this talk 2 or 3 times to make sure that it sounded okay, and who was my advisor over the last 4 years and encouraged me to go and apply to cool places like this. And then in the middle, we have Rebecca, Clay, Carolyn, and Marty, who made the other layers of the sandwich. I only made the 1 layer, the buffer layer was mine, but 4 other people had to make the other layers of the cell, so without them, I wouldn't have even had a research project. So I'm very thankful to them. And then, of course, my 3 corporations that sponsor the research were the National Renewable Energy Lab, which is in Golden, Colorado, the Department of Energy, and Lawrence University. And then I'd also like to thank you for coming to listen to the talk. So this is the end of the talk, and I will now take questions. Yes, Jamie.
Between the different deposition methods, do you have any idea how like the crystal structure or like the structure of these layers varies, and that might play into the efficiency or why some might be working better than others?
I don't know, but I know how to find out. Because I know that if you measure them with an XRD, you could look really closely at the crystal layers, and my mentor, Steve, actually does a lot of this, but I'm not allowed to work with X-ray machines, and I wasn't really there for long enough to do any. So I'm pretty sure that that has a significant effect. I just didn't have time to find out. Ben.
Okay, so with your solar cells, they were each little section was only collecting 1 wavelength, right?
Yeah.
So why were you using a wide band of them, and not just the highest energy, most like a combination of the highest energy and the most abundant one? Because at the beginning you showed a graph of the different wavelengths available.
Yeah.
And
I would go back and it would take forever to go through.
yeah, and I believe UV and blue were there.
Yeah, it was UV and visible and infrared.
Yeah.
Well, because I only get to pick 1 wavelength when I make my cell. And so if I only get to pick 1 out of 400 wavelengths, I want to pick one that's definitely going to hit the Earth's surface. Because I could pick a UV one, because UVA is way more energy than visible, but there isn't as much UV light at the Earth's surface. And so we might occasionally get a high energy particle, but I'd rather pick something that's more consistent. It's going to get 1 particle every second that's at a moderate energy, rather than 1 particle every minute that's really high energy. Because it's better for the circuit to have consistent energy flow. Shannon.
Do you know what kind of deposition method is used to make the cadmium cells?
I made those 2. Those are the same. Those are atomic layer deposition.
Okay.
That one's like the really popular one with the scientists who are old enough to take the training course. But I just didn't like it because I wasn't allowed to use it, and it also takes a long time. Patrick.
Has the cadmium sulfide one has been built with the other method that you found better for the set?
Which one?
Deposition.
The chemical bath. I don't think the cadmium. No, I take that back. It has, because they can do chemical bath with cadmium, and I think the results were similar. There isn't a paper published on it yet because it's a very new kind of thing, but I'm pretty sure that laying down the cadmium sulfate is a little bit worse than the atomic layer, which is why atomic layer deposition is the really popular one for making the really good cells. Professor Stork.
Selenium is pretty toxic too. So
Yes.
do you know if there are any prospects for getting rid of those bad species?
There are prospects, because the cells that I'm making are copper, zinc, tin, selenium. There are also groups that are making copper, zinc, tin, sulfur. So there's the sulfur and the selenium. There's even ones that make a combination, because they're in the same period of the periodic table, so they have pretty similar properties. And you're right, selenium is toxic, but so far no one has managed to completely get rid of selenium and make a cell that worked very well. So there's a reason that they used it for that CIGS. It works really well. Anybody else?
you had mentioned that there needed to be the four elements to it, or the absorber layer, the 1, 6, and 3 plus 3. Why is there only 6?
That's beyond the scope of this lecture. That's all I would say. But to give you a hint, it has to do with the number of electrons that each of the materials have. So depending on which column they are in, they have a different number of electrons in the valence band, the one that's on the bottom. And so I believe when you add up 1 plus 6 plus 3 plus 3, the number of electrons in all of those, you get a full p orbital and a half full d orbital. And half full orbitals are more stable than full orbitals, so it makes a stable material, but the electrons are better able to be excited to the high level. So there are a lot of reasons that you won't all understand, but we've picked those for good reason.
Let's thank the speaker again. So we have a